All right, just to very quickly blitz what we went over last time, we were talking, okay, the problem we were solving is maximize the integer value of an unsigned integer, right? Basically, if we have n bits, what are we looking for? We want all ones, right? We know that's the best answer. We wouldn't use a GA for this problem, but we're using it just for demonstration purposes because it's easy to understand. And it's easy to think about like the search space a little bit, and we'll get to that shortly. And we call these candidate solutions, and then the encoding we call like the chromosome. So how do we want to encode this like bit string? Well, I did it in a list of zeros and ones. Did I have to do it that way? No, I just thought it was pretty easy to do it that way. And then a population is a collection of these chromosomes. So here I'm doing it as a list of lists, right? A list of chromosomes where each chromosome is a list. Here's how we can generate it, just with random, right? This should be trivial for you, right? Population for whatever the population size is, generate a string of that many bits of zeros and ones. Or a list of that, I mean. And then append that to the population and repeat for each member of the population. And then there's evaluation. That is, well, how good is this chromosome, right? So what am I going to do? Is I'm going to go through and basically figure out what the binary, this is just a fancy way of figuring out what the binary value is in terms of an integer that is easy for us to understand. Okay? So that is the fitness that we're going to use. If a number is 7 and another number is 44, 44 is, we want to maximize the value, right? So 44 is better. Okay? And that gives us like the gradient, all right? A direction to go. Gradient just means like a slope, okay? It gives us a direction to go. If I have a 7 and a 44, well, I want to go to the 44, right? Because that's towards better. And how do we get the population fitness? Well, that's simple. There's a lot of ways we can do this. What I did is I just had a separate list that's going to go through. We're going to evaluate the fitness of each chromosome in the population and append that to the population fitness list, right? But the idea is the chromosome at index 0 of the population, its fitness value will be an index 0 of this list, okay? We can do this other ways. We can make the population like full of tuples, where one element in the tuple is the chromosome, the other element is its fitness value. We could make new classes called chromosomes, and each chromosome has a fitness. There's a lot we could do. I'm just keeping it as simple as possible for right now. Now, selection, okay? So to remind you what selection is, remember we start with like randomly generating some solutions. We don't have to randomly start, but usually we start with a random set of solutions, candidate solutions. We evaluate how good they are, and then we need to like pick the ones that are like relatively good to then go on and let them like change a little bit to add to the next like set of the population, the next generation we say. So we need a mechanism to select. Now, we want it to be such that the better or the more fit candidate solutions should be more likely to persist within the population, okay? And less candidate solutions would be less likely, right? They're more likely to die off, as I say it there. So this is not, though, as simple as always selecting the best candidate solutions. You might think, well, just always take like the best ones and use that. But that's not going to work really well. Because what will happen is the population will converge too early. When you're always picking the best, your population's diversity will shrink. And when you lose diversity in the population converges and it has a much harder time exploring the search space more effectively. So we want to be careful to not cause early convergence. And a way to do that is to encourage diversity within the population. And that is, yeah, don't always pick the best ones. We want it to be more likely to pick the best ones, but we want to do it in a way where like, okay, we will get some that aren't as good, but maybe they're different, right? And that differentness is a very important thing. Like there's like, let's say 2 levels of understanding evolutionary algorithms. There's the there's the superficial, like initialization, evaluation, selection, variation operations, repeat, 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 and then finish. But then there's having a really good understanding about things like, well, diversity is actually a really important metric that it's kind of like hard to measure, but we know it's important. So there's a lot of like this like abstract, hard to pin things that are very important to understand to be good at using these tools. And the only way you pick up these tools is by these ideas is to practice. You got a question, or is it just?
No, I just kind of can relate it to actual like biological evolution.
Yeah.
Like fitness being survival level, but depending on a period of time, there could be a different stressor that you're actually.
Absolutely, right? Like you need your populations to be robust to something, right? Like if a new, yeah, of course, right? Of course.
So if you're only selecting fitness based on like the current stressor, then any future stressors might be.
Absolutely obliterate it. Yeah, absolutely. So yeah, we don't want to converge too early. Basically, what I mean by converging too early, just to give you a sense, these are ideas that you will get more familiar with as we go if you're not already familiar with them. Is like usually I'm just going to show like a one-dimensional fitness landscape. Okay, it looks something like this. Okay, and I want to maximize my fitness, and the only variable I can change is along the x-axis. Okay, where I am along the x-axis. So where is the global optimum? Right here, right? That's what we want. But often, can you see this reasonably well, or is this going to help? Okay. Well, the chair's in the way. But what could happen is we might get stuck in a local optimum, where if think of it like this, that's 1 point, right? If we have a population of candidate solutions, they'll be like here, 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 or something, right? They're going to be all over the place. But if for whatever reason we always end up picking some that are over here, over time, the population is just going to get like stuck here. And it's going to be hard because look, a lot of times with the fitness function, we've got like a gradient that we're following. Like, and this is like, look, there's a lot of strategies on how to deal with this, right? But if we're going very naively and just following the gradient, if we're here, we're never going to want to go down that hill because that's further away from where we want to be. But having the bigger picture, we know, well, we got to go down that hill to get up the other hill. But if we converge too quickly, we're stuck. And that's not ideal. So this is where it becomes important to think about the population and not individual candidate solutions. Yes, this is a core principle of evolutionary computation. Look, at the end of the day, if you want to find the best solution to some very hard problem, and you run your evolutionary algorithm and you have a population in the end, let's say you have 100 candidate solutions, you're going to go through and pick the best one, right? But when the evolutionary process, when this algorithm is running, like yes, individuals are evolving, but it's important to think about the whole population in aggregate and how it's changing. It's an important concept. And again, all of this we're going to revisit as we go. This is just intro stuff for us right now, setting the stage. Okay, but focusing on this metric is detrimental to the population if we're always picking the best candidate solution. So instead, we always need to emphasize diversity. And this can be done in some ways, but it's not easy to do. And often, these things can be in conflict with one another, okay? Where like, well, we always want the best ones. Often that might reduce diversity. And it's because, like, our measurement of what's the best is always like based on our like what we think is important, where these algorithms, like we kind of want them to do their own thing to eliminate biases we have. So like what we think is the best is only one dimension of what else is important, which like the diversity is another thing. And if you don't have diversity and you have the best solutions, well, that's your population's in big trouble. It's not going to work at all. Okay, this can be done in a lot of ways, and there are no hard rules about how selection is done. This is going to be a common theme throughout the semester. Evolutionary algorithms is just this abstract idea. It's this framework of initialization, evaluation, variation, selection, termination. It's just those things. How you do them, however you want. Like really, this is one of the things I love about evolutionary computation, is it's hard to do it wrong. Like it's impossible to do it wrong. Because you could just try whatever the hell you want, and if it works, it works. If you think, what if I did this through the evolutionary search? Would it help? Try it, see what happens. There's no rule against any of that stuff. Like when you want to select the candidate solutions, how should you do that? However you want. Now, I will show you kind of like the starting point a lot of people would use, like common popular ones, but they're not necessarily popular because they are good or what you ought to use. They're popular because they are like the elementary things that you always start with. And if you start using evolutionary computation to solve problems and you're only ever using these elementary things that we're learning here today, you're not very good at this. I'm just showing you these things as a starting point. So here is a very simple, very popular, very easy to implement strategy called tournament selection. You randomly select a subset of chromosomes. So you've got your whole population, you select some subset, and then you pick the best of that subset. Done. You've picked one chromosome. And you want to select, if I have a population of like 100, I will do that tournament selection 100 times to fill up a new population, which I will then apply the genetic operators to. So here's tournament selection, population, population fitness, selected indices, direction 1. We will talk about, this looks complicated, it's really not. It's just pick a, you have a question?
Yeah, I was just wondering if the subsets would be like distinct or would they overlap?
You just keep doing it every time. So what you do is, maybe I shouldn't even say subset, like you pick some number. So imagine I have a population, right? Let's say I've got like A, B, C, D, E, F, right? Cool. Right? And maybe their fitness values are like 0, 10, 10, 7, 11, 8, right? We know that this 11 is the best, okay? So what I could do for tournament selection, my population size here is 1, 2, 3, 4, 5, 6. You would have much more than just 6. This is just to show you. So tournament selection would be like, okay, pick, and this is like one of the hyperparameters. How big is my tournament, right? How many do I want to pick? Well, what I do is, let's say I pick boom, boom, boom. So I've got 0, 10, and 11. All right, I'll pick the 11, so E. Okay, great. I've got my new population. I'm going to do it again. Pick 3. A, B, C. B, because it came first. Let's say I pick A, D, F. Well, I get F, right? Because it's got an 8, right? I could, depending on how you implement it, maybe you pick D, 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 right? Maybe you do. You could implement it such that it's impossible to pick the same number twice. You could implement it such that you can. Doesn't really matter in the end of the day. And if I do that, well, I get D, right? And so on and so on and so on. And I do that until I have 6. So let's say I do it again and I get like B and C. There, that's my next population, okay? That's the idea. I realize half of you probably can't see that again. But like I do that process. And this is tournament selection. Yeah?
If you're not duplicating them, you'd effectively just get the same population, just in a different order.
Well, not necessarily, because I could, oh, wait.
If you can't duplicate them, then if you're eliminating ones you already chose, then you get the same population in a different order.
Well, okay, I want to be careful on what you mean. If you mean, like if the first time I pick A, B, C, the next time I do it, I can pick A, B, C, right?
But if you can't choose, like in the new population, you can't add the same.
Oh, absolutely, yeah, you absolutely can. But you're going to want to make copies. Yeah, you would want to make copies. But this is only like the first step, because like then we have the variation, right? So the idea is then like, sure, we may have like D in here, or we have B in here twice, right? If I apply the variation operators, a way to like change it, they should be similar but a little different, right? But we'll talk about that very shortly. here's tournament selection. And you can kind of think about, I just explained this. You can kind of think of tournament selection like, how big do I want the tournament to be? Well, if I make my tournament, let's say I have a population of size k. Well, n. Let's say a population of size n. Not to be confused with the length of the bit strings. I have a population of size n. I have n candidate solutions there, right? What's cool about tournament selection is by picking the size of that subset, we give ourselves a dial to increase and decrease what we call selection pressure. Basically, how likely are we to pick the best ones? High selection pressure usually means lower diversity. Lower selection pressure means higher diversity, usually. What I mean by that is, if I have a population of size n, I could say my subset is n, where I pick n, okay? And let's say they're always distinct, so I pick A, B, C, D, E, F. If I do that, I'm always going to pick the best one, right? Meaning selection pressure is maxed out. If I made my subset, let's do the other extreme. If I made my subset 1, well, I'm effectively randomly picking, right? Like I pick A, C, B, like whatever I pick just automatically goes. If I pick 1, take the best one, there's only 1. So that would mean very, 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 very low selection pressure. So you've got a dial you can play with. Often you're going to see a tournament of like size like 2, maybe 3. So it's actually usually keep it pretty low. But this is something you can play around with, and there is no such thing as one size fits all for evolutionary computation. No such thing at all. Now, when I was saying though, let's go back a second because I think this goes to what Kate was asking a moment ago, is like let's say I pick, and maybe this isn't quite what you meant, but did we kind of like address your question? Okay, cool. It is, depending on how we implement this particular algorithm, we might say, okay, pick 7. And we could just get really bad luck and pick C, 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 C. Take the best. Well, it's C, right? So in that case, we're not actually always guaranteed to get the best one because maybe by dumb luck, but that all comes down to implementation. Let's see, what do we have here? So I do choices, right? So I think, I don't know, I'd have to look up what choices is how I pick my subset. Choices. Let's check. This doesn't really matter, but. No, I want the actual documentation. With replacement. So I'm pretty sure that means we can pick the same thing multiple times. So in this case, cool. But should it be that way? No, it doesn't matter. Whatever you want. Really is whatever you want. And maybe you don't kind of, like you're probably not going to see it yet, but like because evolutionary computation really is such a high level, very loose framework, it allows you to like be as creative and have as much fun as you want with what you're doing. Do whatever the hell you want. That's why I love this stuff, because you really just get the freedom to just hack around and see what works. And there's also that like little bit of a surprise, like when you run these algorithms, they take a little while to run, right? Depending on how big it is. It might take, let's say you do a run, maybe it takes 5 minutes, and that's not very long. But let's say it's 5 minutes, you hit run. And then like the whole time, like if you made a change and you're like, I hope it's better, after that 5 minutes, you're like, oh, come on, let's see. It's like Christmas. You're opening a present. Like, did it work? Yay, nay? Yeah. So there's always some fun to that too, I always found. Okay, now the variation operators. Like, by the way, in terms of run times, when I did my PhD, I was using heavy-duty evolutionary computation for some work. And I used Compute Canada, where I just had a massive number of computers and processors that can run my evolutionary algorithm. At the end, I racked up over like years and years and years and years and years of compute time. I can't remember how much it used to be, like how much it was, because you used to be able to log on and see, but now I can't see it anymore. But I remember it being an absurd number, so much so that when I got the job here, So we have like a local ACENET rep or Compute Canada rep. They wanted to meet me. That's not a joke. They'd be like, we needed to meet the guy that used this much compute time. So it was pretty neat. They can take a while to run. And that's one of the problems with evolutionary computation is it takes a lot of resources to run these things. But sometimes it's our best shot, right? We're throwing everything at the wall and hope something sticks. That's why you use these tools. You don't use them when you have better options. All right, variation operators. These are often called like genetic operators, and they are used to alter the chromosomes in some way. And often there are two broad categories of variation operators. Also, as a note, what I am describing right now is what we call like a generational evolutionary algorithm. There is a slightly different style called what's it called? Why am I drawing a blank right now? I just had it in my head. I can't remember. It's like continuous. That's not what it's called. A steady state, whatever. Where you don't kind of like do selection to fill up a whole new population, is you do selection, then put them back in that same population. But then there's like another selection that's required where you have to like, well, if it's a fixed size population, who gets removed, right? If I select someone and I modify it and I want to put them back in, someone's got to go. So we're not talking about that, but in general, I do this generational strategy. I find it easier and I find that it works better, but do whatever you want. More on that later. I'm just letting you know. All right. Like most things with GAs, there's no real hard and fast rules on how you got to do these things. Typically, there should be a way to exploit. There's like two key things that we like to talk about with our variation operators. There's like exploitation and exploration, where the idea is with exploitation is you want to take something that is already good and like modify it. Because like, look, if we're already starting with something good and we modify it, maybe we'll get better, right? And then there's exploration where, okay, I want to make sure we can like make significant enough changes that we can explore more of the search space. Basically, in that example here where we were stuck here, with exploration, we want to be able to like make those bigger leaps, okay? Depending on who you talk to, we will get into this a little bit more when we get to the variation operators topic. But depending on who you talk to, they will say like, well, crossover is explorative and mutation is exploitive, or vice versa. And there will be flame wars arguing with it. And what I say is they're both wrong. And I'm right. It depends on what the actual nitty-gritty is of each thing. Some crossovers that we're about to talk about are more exploitive and some are more explorative. It really depends. And making categorical things like that is just wrong. So more on that later in the course. That's a whole theme of today's topic. Crossover is the idea where, and this is one of these, this is like a jargon word that we've stolen from biology and we misuse. But it's the idea that if we have a candidate solution that's good and another candidate solution that's good, what if like I kind of like cut them in half and swap the parts, okay? Right? If they're both good and they're both good, and I kind of mix them together and pull them apart, maybe I get more good things. Maybe I don't, whatever. But that's the idea of crossover. And that would be an example of a very simple form of crossover, but that doesn't mean it's not good. It's one-point crossover. Take two chromosomes, randomly select an index, swap all elements after that index. There, perfect. Okay? So let's say we pick these indices. After performing crossover, we get that. Perfect. That's the idea. You're going to have two-point crossover. Guess what that would look like? Well, you pick 2 points and then swap between them, and so on and so on and so on. And here's how you could do one-point crossover. Make a copy of the parents. You always want to make sure you're making copies. If you start messing with references, you're done. right? So you always want to make sure you're copying everything. And if you don't remember, this is just a shorthand way of making a copy of a list in Python, right? You slice the whole list, it returns the whole list. So make a copy. It looks like when I call this, I give it the index I want to perform crossover on. Whoops. And then I copy everything from the index to the end, and then from the index to the end to child 2. This is a very Python-y line of code. You can do this, right? Like, you know how when I'm teaching intro to programming and I'm like, how do you swap the contents of two variables? And you're like, well, you need like that third variable. You go like.
Or you can do XORs.
We're not talking about that one. So where you do that thing where you go like this to swap, right? Like that's how you have to do it. And then some asshole in Python shows up and says XORs. Or they do effectively this, where you're like, well, A, B equals B, A. And you're like, oh, I did it. I didn't need that third variable. And you're like, fine. Okay, fine. But you want to know what your computer really did under the hood? The same thing. So there we go. Anyways, that's what we're doing. This is just a very Python-y way of doing one-point crossover. If that's not clear to you and you're like, I would rather write more explicit code, less Python-y, more power to you. I actually encourage that. Typically, I don't like Python-y code, but in this course, I decided to try to use Python-y code. And I still, after doing it, I still don't really like Python-y code. When I say that, what I mean is I prefer to write code that, like if you've never seen Python before, but you've programmed in Java a lot, you'd look at this and be like, whoa, I mean, I know, like, what? Right? There's a lot of weirdness here. Usually I like to write it in a way where I'm using the Python code to do the same thing as this, but in a more like, okay, select the index. Here's the for loop. Copy the contents over. Like a more direct way. Because then if someone's never seen Python before and they have like C++ experience, they can look at that code and be like, I know what's happening, right? I find Python-y code isn't as self-descriptive to a general audience of programmers, but here we are. Deal with it. Okay, so the function only returns 2 chromosomes. That's not really true, so it must return multiple times. So you're like, yes, it's returning 2 things. Well, not really. It's returning 1 tuple with 2 chromosomes in it, but that's perhaps pedantic. So if I have a population size of like 100, right, and I do crossover, well, crossover was only ever applied to like 2. So I'm going to want to like do this a bunch of times for like all the things in the population. So here we go. Here's what I'm doing. I'm saying for I in range 0, population size 2. So I'm always actually selecting pairs. And I'm selecting the pairs based on their adjacency. Doesn't really matter, but it's pretty easy to do. So I'm counting by 2s. I pick a crossover point. I pick a random index from the bit string length. Okay. I perform 1-point crossover. Ah, wait, this line right here, I almost forgot. If random is less than crossover rate, we often set, so we want these variation operators to be applied probabilistically, which is a fancy way to say, like, not all the time. Okay? So maybe what I would say is like, okay, here's chromosomes 0 and 1 based on their indices. Okay? Roll the dice. Do I or do I not actually perform crossover? If I roll the dice and I do perform crossover, I modify them. If I roll the dice and this isn't true, I just skip them. Because we want to make it such that some of the selected candidate solutions remain unchanged. They don't have to have crossover applied to them. So that's the idea there. Usually, like if you're starting with a genetic algorithm and you're setting your parameters for the first time before you start like tinkering with these values, usually for crossover for a GA, that's going to be like 80%. So there's like an 80% chance that you're actually going to apply crossover to that pair. And then you're going to look at the next pair, then the next pair until you get to the end. All right? Yeah. Potential problems. So let's say, for example, actually here, let's just go like this. Okay. think about what I just showed you in terms of 1-point crossover. This is a population where n is 5. Well, okay. We have 1, 2, 3. We have 5 members of the population, and the bit string lengths are 1, 2, 3, 4, 5, right? So we know what the best answer is. 1, 1, 1, 1, 1. Okay? Let's say this is our population, and we're applying crossover. Can you look at this and see any problems? What do you see?
There's no ones in the second, in the first, index 1.
Yeah. There's no ones here. And why is this important? It's important because no matter how I apply 1-point crossover, I can never get a 1 in there. Right? Meaning I'm doomed to never find the best answer. And that's a big problem. So we have to be very careful about these types of things. This is easier said than done. Now, it's not like you're like, okay, I have to be careful of the crossover. Well, you have to be careful of the crossover, the encoding of your problem, and a billion other things that you have to kind of think about, on top of the fact that if you're actually using an evolutionary algorithm to solve a problem, you don't understand the problem that well enough to be able to go like, oh yeah, look at that, we're missing. We only have that luxury right now because the problem is so simple and we understand it. Oh, there's no way to get a 0 in there. But if you're trying to program a robot to walk with an evolutionary algorithm, you're not going to be able to be like, oh, we got a problem. No, it's too complicated. You'll never know. So it's a bit of a fool's errand to go and look for that. Maybe you can magically figure something out. But it's important to be aware of these things because you want to have a nice balance. So how can we address this particular situation? Well, we're going to use something called mutation. Now, mutation doesn't exist to fix this problem. Mutation exists as its own thing, but can also fix this problem, depending on what the mutation strategy is. A mutation is a variation operator that is applied to a single chromosome at a time. But we're going to do it the same way as crossover in the sense that we start at the beginning and we roll the dice and be like, are we going to apply mutation? Apply mutation? Apply mutation? And instead of pairs, we just look at them individually. Okay? And I think usually with mutation, I think you're looking at 20% mutation. Okay? But there's a lot of things you can play around with that. Usually as your population converges, you might want mutation to go up, so you might have these variable mutation rates, but that's a future problem. So we could do something called a bit flip mutation, the simplest form of mutation. Here's how we do it. Select an index. If it's a 0, make it a 1. If it's a 1, make it a 0. Simple as that. Bit flip mutation. Cool? Cool. And hopefully it's now obvious that this could actually solve that problem because bit flip mutation might pick index 1 and flip it. And then suddenly we add a 1 to the population. So here's bit flip mutation. Make a copy. And then this is just a fancy way to do bit flip. Add 1 mod 2. Right? If it's 0, you add 1. 1 mod 2 is 1. If it's 1, you add 1, you got 2. 2 mod 2 is 0. Right? Again, this is kind of someone could sit here and be like, I think it's more self-descriptive if you say if it's a 1, make it a 0. If it's a 0, make it a 1. Absolutely. I would never argue with you about that. You're absolutely right. But whatever, I did it that way. Okay, and how do we do that? Same idea. Mutation, pick a random index, apply it, and then add it to this mating pool. By the way, I've created this mating pool variable. I don't think I talked about it yet.
It was up.
It was? Well, I think we actually explicitly get to
right
it.
After the...
Here. I'll be able to explain it right here anyways. Termination requirement. When do we end? Well, that's up to us. You could say run until I find the best solution. Run until I find a solution that is beyond a certain threshold. Run for no more than 10 minutes. Run for some number of generations. Run until the certain diversity level in the population is below a certain threshold. Run until there's been no meaningful improvement in fitness for the last 20 generations. Whatever you want, you can do. It doesn't matter. As long as there's a method to your madness. What I like to do is the simplest thing is pick some number of generations. That's it, right? And when you run it, I don't know, let's say 1,000 generations. You wait, you get some results, then maybe you let it run for 10,000 generations. Did you get anything better? If you did, well, let it run even longer, see if you get something better. You don't really know how long it needs to run. But if you run it for 1,000 and then you run it for 10,000 and you get really no difference, well, now you're just wasting time. Your population usually seems to converge before that. Maybe you can get away with running it only for 100 generations. I don't know. Okay, so here is my whole thing. By the way, these little comments here, they are comments, but they are actually acting more as like tags. Sure, they tell you like, well, there's the evaluation, great and all. But when I generate this website, I say, like, for example, the mutation thing here. When I generate the website, this is actually from code that you could run, like that's on the GitHub page. It specifically says like, okay, go select all of the contents between those two tags. So the tags are there, great and all, but they're actually really more there for populating the website in a nice way. So let's look at the whole thing, right? So this is assuming we've already started. We already have a population to start with. There, for generation in range generations, population fitness. For chromosome in the population, calculate the fitness. Perfect. Bookkeeping. This right here, I'm just doing some bookkeeping where I'm saying, I don't know, get the best fitness and then get like the average fitness of the population. Just for, I'll keep a list of this for each generation. I'll have like a data point, right? And then hopefully over time, I can see something that like, assuming I want to maximize values, I get something that's probably going to look like this, right? That's what I want to see, right? And then your average probably looks something like this as well, right? We saw an example of this idea back on when we saw those evolving cars, right? So that's the bookkeeping. Now do selection. That's where mating pool came from. So what I do is I create a mating pool where I do selection. Then I go and see, do I like do the crossover, do the mutation, and those are done on like all of those things are added to the mating pool. And then when we're done all that, the population becomes the mating pool, right? So then we repeat, okay? So like population is the current population, mating pool will be like the next generation's population. Why did I call it, like mating pool isn't like a specific jargon, that's just what I called it. You can call it whatever you want. You can call it next generation, I don't know. Cool. So notice that this generation loop performs evaluation, selection, variation. That loop, right? And notice the bookkeeping, yeah. Also notice the tags, you could ignore them. Once the loop terminates, the population, now depending on how we implement these things, remember that the last thing we do in that loop is reassign what the population is. And the first thing we do in the loop is evaluate the fitness. Meaning when that loop ends, that last population's fitness will have never been evaluated, right? Because we didn't go back to the top of the loop, we just stopped. So based on how I implemented it, how you do it, it could be entirely different, but based on how I did it, I gotta calculate the fitness one more time, and then I print out the population fitness, print out the population, generation max fitness, whatever, 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 and there we go. Cool. There we go. And by the way, you could go download this code straight from, whatever, weird. What? Yeah, download insecure files, great. You can trust me. I didn't give you, where, do I not have Notepad++? Whatever. Come on. I didn't know Notepad was so hard to open. There, right? So here is that GA, right? If you go down to the bottom, you'll see some commented out things. That's just there to play around with later, where I like plot some of this stuff. But yeah, you could download this code yourself. In fact, that's what we're going to do. though we don't really have the time to really get cracking today. But let's see, what do I say for the next topic? Experimenting with the GA. Perfect. So, raise your hand if you've got Python on your computer. Cool, great. Here's what you're going to do. Raise your hand if you have GitHub Desktop on your computer. Well, you don't. If you don't, look. You don't have to use GitHub Desktop. Most people like GitHub Desktop. Then if you like more power to you. I often make so many mistakes on GitHub Desktop because I'm not used to it, and I always mess it up because I use the command line. But if you've got like GitHub, raise your hand if you don't have a GitHub account. It's fine if you don't. If you don't, make one right now because you're going to need it. So that means everyone has one. All right, cool. So I'm going to go here and sit for a second, and I'm going to kind of show you what I want you to do. And I want you to do this to be ready for the next lecture. All right, so if you go back to the main page, at the top of the main page is a link right here. The content used to generate this course can be found on GitHub. You click it. Okay, there we go. This is the content for the course website. And I've actually got some pull requests I need to merge. I'll deal with that later. They're Dependabot. Anyone know what Dependabot is? Yeah, a couple people. Basically, if you've got software, Dependabot will run like once every so often and be like, was there any updates? Should you update your software? You know, like, oh, matplotlib was updated, right? That type of stuff. What was updated? Download artifact, checkout. Matplotlib was updated. Look at that. Huh. Anyways. Here's the code.
Does it check if like what you use in your software would actually work with that new version?
It does some amount of like some stuff, I'm pretty sure. But usually what you would do is like, for example, this is just good information because we're going to be using GitHub. Like on this website, for example, if you scroll down, oh my gosh. Yeah, and it's going to make me authenticate. Oh my goodness. Where's my, 523208. There, okay, now I'm logged in. Much nicer. Okay, if you were to go like here, by the way, you can have like custom actions, and I have some, and it'll run those actions, and if I go here, it'll tell me that like, okay, it ran the tests, and it could like build the website, meaning that nothing crashed with this change, meaning I know it's fine, right? So you would usually have things like this. These are actually relatively simple to set up, but if it's the first time you're doing it, it's a little overwhelming. This is not something you need to deal with. But what's nice about this is, by the way, let me take a step back. Here's what you're going to do. Who here is, on a scale from 1 to 10, at least 3 out of 10 familiar with GitHub? Okay, that's fine because I don't think we're going to get to it today. So that's what we will do on Monday. I think we have lecture where I will kind of like work you all through on how to get it up and running. For those of you that are already comfortable, I want you to fork the repo and download it on your computer and get it like there running. I also want you to read the README. Of course, you didn't need a reminder for that. And you're going to set up your virtual environment, okay? For those of you that raise your hand if you don't know what a virtual environment is. So everyone knows that apparently. Okay, well, I'm going to explain it again anyways because I don't believe everybody, but basically you've got Python on your computer, right? And we were talking about different versions of things, right? So you've got Python on your computer, right? And then you've got a project that requires Python version whatever, or maybe matplotlib version whatever, or NumPy version whatever. But here's a problem. You also have, you have Python version, you have NumPy version 6.1, I don't know, right? I have no idea what's current, right? 6.1 on yours. This thing over here requires NumPy version 6.0. And this thing over here requires Python or NumPy version 6.0.2, right? So we got a problem. So what we do is we make these virtual environments where you basically say, okay, we've got our pure, our clean, whatever normal Python install, but we're going to make a special little environment and pretend it's empty. And we're going to install all of the dependencies that this software needs, and it's only going to exist in its own little bubble. Meaning it's not going to screw up the version you have or the version some other software needs. It's going to make like an isolated little version of Python that's going to be happy. If you run that, this creates the environment, this activates it, this says run the install script. I've got an install script that will go and download all of the dependencies you need for this course like that. So you don't need to go hunting for yourself. Isn't that nice? So you do the README. I show you, here's how you would do it in Windows. Here's how you would do it in Bash. If you have, raise your hand if you're on a Windows computer. Okay, so these computers are Linux. And you should be able to log in and use them too. If you're on Windows, if you can, if you don't have to, but if you can, you might want to use the Windows subsystem for Linux, right? Which is really nice. And the reason for that is a lot of software development, it's everything is so much better on Linux. Okay? It really is, right? That's not it's fine on Windows, but it's better on Linux, right? You could do this on Windows just fine. I'm going to do it on this computer just on Windows. It'll be just fine. But in general, you might have a nicer experience if you use Linux somehow. All right. So you would run these things and you'd get all set. And when you clone the repo, you will actually also get all of the course notes that you could actually have locally, so you don't need the website anymore, which is kind of cool. But you will get all the software that you could then run easily. Yeah?
Is there a reason you want us to fork it?
Because I don't want you making changes and accidentally pushing to mine if I don't want you to.
Well, I mean, we couldn't push. We don't have access.
Oh, I know. I could give it to you, but it's better to have a fork because what I want you to do too.
We're not gonna make any changes.
But I kind of want you to make changes, right? So what I would love, in a perfect world, what I would love is for you to be there's a typo right there. And I want you to fix it. And then
then I'll fork it.
Right? And then ooh, that's cool, right? Or maybe you're this is just explained like shit. I want to fix it. Do that. Or oh, what about if there's a change that you think is a good idea, fix it. You don't have to worry about breaking anything. I've got those actions that will make sure everything's fine. And I have to read your change to confirm. So if you do make a breaking change that gets added, it's my fault, not yours. So you don't really need to worry about that. So yeah, there's that anyways. So here's what we will do next time. If you don't do it already over the weekend, you're going to want GitHub on your computer. If you like the command line interface for GitHub, where you type git status, git clone, blah, 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 more power to you. All right? If you're really not that comfortable or familiar with it, I would recommend, if you're on Windows at least, because I don't know if it's available for Mac, I assume it is, but I don't know, is the GitHub desktop. It's this GUI client that is pretty easy to use. But I'll warn you, if you're used to the command line interface, if you're like me, I make a lot of mistakes on GitHub desktop that I wouldn't make in the command line interface just because I don't use it very much. But get that. And if you're on GitHub and you fork, on your GitHub desktop, which you would log in on, you'll have the ability to be clone the repo locally, so you have it on your computer. And then, so we're going to do that. And then you run that README, you open up terminal or whatever, and you run those that README to get you're up and running, and you're good to go. You're all set. You will see that I'm going to be using PyCharm as my IDE. A lot of the things are set up in a way for my PyCharm thing. You don't have to use PyCharm, but I feel I remember people last semester or last year who were using VS Code or something, kind of had a bit of an annoying time. And what I say to you is that's your problem and not my problem, because I'm using PyCharm. Any last questions? I do recommend you try to get set up over the weekend yourself. You can't break anything, don't worry. And yeah, otherwise, have a wonderful weekend.